Here we are back for part 3 of 11 parts. We're still looking at sine and cosine. We'll be talking about using the nature of periods and what else? Horizontal compression or expansion. So we won't do a whole lot today. We'll start with, I don't even want to pronounce that. I wrote it, but I don't want to pronounce it. Periodicity. Periodicity. No, periodicity. Oh, forget it. All right, I should never have used the word. I can't even pronounce it. Okay, the imaginary I from Algebra 2. Well, we know that it wasn't imaginary, but one thing we did notice about it, remember this? It was defined as the square root of -1. So if we square a square root, what do we get? We get the radicand. So this would be -1. And then if we cube the square root of -1, we end up with, okay, let's try it. I cubed is the same as I squared times I. That's I, of course, to the first power. Remember, when the bases are the same, the exponents add, so you have 1 and 2. So that's the same as a -1 times I. So we can say this is -I. And then if we have I to the 4th, whoops, I to the 4th, it's the same as saying I squared times I squared, which would be -1 times -1, which would of course be a +1. Very nice result. So +1. If we have I to the 5th, that's the same as saying I to the 4th times I, which would, of course, resolve to a 1 times I, and 1 times anything is whatever it was, or back to this, come on, which is the same as I, and then we've got -1, -I, and a +1, and then we're back to I, -1, -I, +1, and so forth. Oh, -I and 1. What powers of I will equal 1? Well, 4, 8, right? 12, 16, 20, 24, and I could keep going on like that, couldn't I? What do we notice? These are all multiples of 4. Oh, what about I to the 0 power? Could we even do that? I don't know. 11 segments. By the time I get to number 11, I'm really going to be silly. Okay, what does I to the 37th power equal? Well, it certainly equals I to the 36th power times I to the first power, right? And 36 is an even multiple of 4, isn't it? 9 times 4 gives you 36. So that would be the same as 1 times I. It's equal to I. So it just keeps cycling through as we add 1 to the exponent. Now we can use the nature of periods to help us out with our trig functions also. We know that the parent graph, sine, has a period of 2 pi. And we can use that when we go to figure out what this is. It doesn't seem possible that we could solve this without a calculator. It really doesn't. But I'm here to tell you we can and to show you how to do it. First of all, we're going to look for multiples of the period. Even multiples of the period. So what would, we've got this over 2, what would 2 pi equal if I did this? If I multiply the denominator by 2, I have to multiply the numerator by 2. That would be 4 pi. So if I make this some multiple of 4 pi over 2, I can actually just get rid of it because it's going to represent a full revolution. And every revolution just takes us back to the coterminal angle. If I take 1 pi over 2 out, I'm left with 57,800. Let's see, would 4 go into that evenly? We're going to try that. 57,800. So 4 will go into that once. And then we've got 17 goes in 4 times. Leaves us with 18 goes in 4 times. Leaves us with 20 goes in 5 times. Okay, so it is even with no remainder. So we can delete the multiples of the period. So those just disappear. Let's see, that's right here. Oh, I had all that already done for us here. Now, this is a coterminal angle, pi over 2, which is right here, isn't it? It's a 90-degree angle. And what is sine? Think of our unit circle. At this point, we're 0 with our x and 1 with y. So sine is equal to 1. So there we did it without using a calculator. Find each of the following without a calculator. All right. Now, I cannot just combine these two, unfortunately. But I can remove multiples. Cosine has a period of 2 pi. So I'm going to look for periods of 2 pi in this one. Cosine, clearly 288, which is a even number, can be divided by 2, and that'll leave me with the cosine of 0.45 pi minus the cosine of, and the same thing's going to happen here, right? Multiples of 2 pi and end up with 0.45 pi. Ooh, well that's interesting. Now these are even. So I end up with 0. So the answer to this is 0. How about this next one? Pi over 4 minus 900, oh my goodness, 99,999 pi. Well, tangent has a period of only 1 pi. We're going to look at that more later. So all of these can disappear, and I end up looking at the tangent of 45 degrees, or pi over 4, which is which is 1. I could draw it over here. That would be 45 degrees. To look at it on your unit circle, and we know tangent is y over x, so 1 over 1 is 1. The reciprocal of the period yields the frequency of the cycle. Okay, that makes sense. Reciprocal of the period. So in the case of this one, y equals tangent, and our frequency would be stuck right in here. B equals 1. This is where B would go. So tangent of 1 times our angle measure. And what is the period of tangent? We talked about it just a moment ago. The period of the tangent cycle is pi. So the reciprocal of the period would be equal to 1 over pi. So that says the frequency of the cycle is 1 cycle per pi radians. And that's exactly what we see with tangent. We start from negative infinity at negative pi over 2. We move up at 0 to a ratio equal to 0. And then we go on to positive infinity as we approach pi over 2. What is the distance from negative pi over 2 to positive pi? And our frequency is 1 per pi, and that's our B, which goes right there. Okay. As the frequency of a cycle increases, we start seeing it cycling in a smaller period. The graph shrinks horizontally and the period gets shorter. So we'll give an example of that. If I have y equals tan 2 times the angle measure, we've doubled our frequency, haven't we? And you'll see that. Let me get a highlighter. If we look at the parent, which had a frequency of 1 per cycle, and now we're looking at a frequency of 1 per pi. Now we're looking at a frequency of 2 per pi, right? So the frequency has has increased, the graph has shrunk. It has shrunk, squeezed it right in there. I can see twice as many cycles in the same window. And the period is now pi over 2. Frequency doubled, period is now pi over 2. And of course we're going to look at what happens when the frequency of a cycle decreases. So it's cycling less often, so the graph is going to stretch out. Right, it's going to stretch, and the period is going to increase. We can see that here. If I highlight the same section of the window that we've been looking at all along, we only get half of the full cycle. So the period has clearly increased here. Let's look at the numbers. We have the frequency. See, the B is equal to 1/2 now. So now it's 1 per every 2 pi. Our period is 2 pi. Let's do it for sine. Oops. Didn't mean to do that. Hit the wrong thing, sorry. Okay, here we are with the parent graph. What's our frequency? It's 1, right? And we know for our parent graph the period is 2 pi. That's what we ordinarily see. Now, if we start messing with this frequency, what is this frequency anyway? It's 1/3. Let's get this out. So now our period becomes 2 pi divided by 1/3, or 6 pi. A horizontal stretch of the parent graph by a factor of 3. So what happened to the frequency? It is only 1/3 of what it used to be. This will stretch it out and increase the period by 3. So it went from 2 pi to 6 pi. The other thing that's happened here, I didn't speak about it, but we have a negative on the amplitude, which causes this to reflect across the x-axis. So sine, which would have been going like this, reflects and now goes, still crosses at exactly the same place, but its valley becomes a peak and its peak becomes a valley. The third example here shows a lot of things happening. Let's see if we can make sense of that. I'm going to focus in here first. We've got a frequency that is doubling. If we cycle twice as fast, the period's going to be smaller. And sure enough, we divide it, the 2 pi, what we usually expect with sine, and we have a period of 1 pi. The other thing that's happening is we've got a negative here. A negative on the input, very different than having a negative out here. It's a negative within the operation. that's going to reflect across the y-axis. So what's happening? We get a horizontal shrink when we double the frequency. It's only going to be, the period's only going to be half what it was. Oh, we get a vertical stretch. I didn't even say anything about this. I didn't say it up here either. Vertical stretch of 3. This one I didn't mention. We had a vertical stretch of 2. This is right from your notebooks on your calculators. You can graph these curves in degree mode. Your smallest angle that you want to view is going to be your x-min. The greatest angle that you're going to view is going to be your x-max. So you're going to go from 0 to 360. Notice you're working in degrees here. The space between the x-axis ticks, let's see, 0. We've got 1, 2, 3, 4, 5 to get to 90. What is that? 90 divided by 5 is 40. That's 18. Seems a little weird. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. But that's what it is. At least in these diagrams, we're seeing that that is 18 degrees. So if you want to match exactly to what your book is showing, that's what you can do. And set your y-min and your y-max. So we actually don't have any amplitude changes here, do we? It's all of these are an amplitude of 1. And the space between the y-axis ticks, well, what they're showing here is 0.5. So we're going from -1 to +1. The coefficient of the angle variable, that, what are we talking about there? Right here. That's a 1, 2. This is a 1. This is a 4. This is a 1 and 1/2. So what are we seeing? This one is your parent. Okay, this one is your parent. This one is your parent. So you can see what's happening. I'm going to erase. We're just muddying it up. So for these two are being graphed over here. What happens when we double? It cycles twice in 2 pi instead of only once. When we put a frequency factor of 4 in, it cycles 1, 2, 3, 4 times in 2 pi, or in 360 degrees. And what happens when we put in 1/2? It only gets halfway through its cycle in 2 pi. That's pretty straightforward. Frequency in 360 degrees, when that number goes up, the period of the curve goes down. The period is the number of degrees or radians the curve takes to complete one cycle. So you can put down either in degrees or in radians what the parent graph's period is, and then just divide by whatever this frequency number is. We define the horizontal stretch in this way. If the period is less than 360, that's compressed, and the frequency, B, is greater than 1. If the period is greater than 360, then that's elongated. I should have done this. And the examples of that are the compressed are right here. Think of it like a spring. If you think of it one hand here and one hand here, pushing this in so that it's much more compressed. Or elongated, you actually pull it out. This one goes like this. We stretch it out. Period is greater now than 360. Looks like it's 720 degrees. The frequency was less than 1. In this case, it was 1/2. The 5 critical points are at 0 degrees. At the end of the period, midway, a quarter of the way, and 3/4 of the way. That hasn't changed. Those are the critical point angles. You're going to work on this. I'm going to let you do this on your own. You can either do it at home or you can do it when you come in. Let's see what else I've got coming up here. Yeah, I've got one more. So it might be good to, you've got the time, it might be good to work on this one. I'll spend a little time with you. The curve is cosine 2x. Now, we know ordinarily the period is 2 pi, but now it's cycling twice in 2 pi, so the period is going to be pi. What have we done to that? Have we compressed it or elongated it? Let's go back a moment. This one, when we doubled the input, this is the frequency, what happened? It compressed. Same thing for cosine. And our critical points, well, we go from 0. All of these, we're going to go from 0. Why not fill in the things that we already know, right? And the end point is going to be pi. The midpoint is going to be pi over 2. This will be pi over 4, right? Midpoint of that. And this will be 3 pi over 4. This one, which is got a frequency of 3. Ooh, what's that period going to be? It's going to be 2 pi divided by 3. It's kind of an unfortunate number, isn't it? But 2 pi divided by 3. What's happened? It's compressed. As long as this number is greater than 1, it's going to be compressed. We could go right down and figure them all out. Compress, 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 elongate, elongate. Don't get tricked by this one. This one is a fraction, but it is greater than 1. So this one will compress, and this one is going to compress a lot. Please note here, after you've figured things out, you can check it with your calculator. Okay? We'll look to this one. When we put both amplitude and period together, let me just jump down to, let's try this one, E. You can do the rest of them yourself. and you can do them in class. What would the amplitude on this be? We take the absolute value, so the amplitude is 3. What is the period? It's going to be 2 pi divided by the frequency of 6, so the period is pi over 3. What are the critical angles? Well, it starts with 0 and it's going to end with the end of the period, so that's going to be pi over 3. What is the midpoint going to be? Pi over 6, right? Half of pi over 3 is pi over 6. And half of that again is pi over 12. So this will be 3 pi over 12. Oh, really? 3 pi over 12? Well, probably shouldn't write it that way because 3 pi over 12 is the same as pi over 4. Pi over 4. What's the shape of this one? Notice we've got a negative here, so this is not normal. This is reflected. Vertical depends on the amplitude. This is going to be stretched. Horizontal depends on the frequency. It's got a high frequency, so it's going to be compressed. Okay? You can do all the rest. We'll see you back in class. I'm looking forward to seeing you.